You ever look up, see a jumbo jet just cruising by and think, how in the world does that work? I mean, how does something that massive, that heavy, not only stay up in the air, but, stay in one piece? Well, in this explainer, we're going to pull back the curtain on the invisible engineering that makes it all possible. We're getting right down to the bones of it. Okay, let's jump in.
All right, so this is the big question, right? How does a 400-ton aircraft, think about that, that's basically a flying building, stay together when it's battling winds that are pretty much hurricane force? The answer, and this is the really cool part, isn't just about brute strength. It's about some seriously smart engineering. Okay, so where do we even begin? Let's start with the absolute basics, the body of the plane, the fuselage. And right off the bat, here's a key idea to hang on to. An airplane's body is way more like a human skeleton than it is, say, an eggshell.
See, some of the early designs were what you'd call monocoque, and that's exactly like an eggshell. The hard outer skin does all the work, carries all the load. But the problem with that, it's super heavy and not very efficient. So what we use today is a semi-monocoque design, and that's our skeleton analogy. You've got a thin, lightweight skin, but it's reinforced by this whole internal framework. It's just a way smarter, stronger, and way lighter way to build.
And a super critical piece of that skeleton is something called the longeron. The easiest way to picture it, it's the airplane's spine. Seriously, it's this massive beam that runs all the way from the nose to the tail, taking on the major bending forces and basically tying the whole structure together. It is the backbone of the fuselage. Now, all this talk about skeletons and lightweight skin brings us right to the fundamental dilemma of building anything that flies. It's this constant, endless battle between strength and weight. Every single design choice is a delicate dance, a compromise.
Yeah, there's no such thing as a perfect design. The best you can hope for is an optimal compromise. I mean, think about it. The engineers are in this constant balancing act. You want to make it stronger? Okay, but that's going to add weight. Want to use fancy new lightweight materials? Great, but your costs just went through the roof. And what about a really complex design? That might be a total nightmare to actually build and then keep in service. So every single plane you see flying is a masterpiece of juggling these trade-offs.
And just to give you an idea of what a manufacturing nightmare could look like, let's talk numbers for a second. Take the classic Boeing 747. It's made of roughly 6 million parts. 6 million. Let that sink in. The complexity is just mind-boggling.
But here's the kicker. You ready for this? About half of those parts, we're talking 3 million of them, are just fasteners. That's it. Rivets, bolts, screws, all the little things. These tiny overlooked pieces are literally what's holding that entire 6 million piece puzzle together at 35,000 feet. No big deal, right?
So obviously, picking the right material for each one of those millions of parts is absolutely critical. Engineers use this whole cocktail of different materials, each one picked for a very specific job. You've got aluminum, that's kind of the workhorse, right? It's great for the fuselage skin because it's light and pretty strong. Then you bring in something like titanium, where things get really hot, like around the engines. And then you have modern composites, which are just these incredible materials. They're insanely strong for how little they weigh, and you can even design them to be strong in one specific direction. It's amazing stuff.
And if you want to see this in action, just look at a modern plane like the Boeing 787. A full 50% of its structure is made from composites. 50%. That massive shift away from old-school metals is exactly why these new planes are so much more fuel-efficient and can perform so well.
Okay, so we've got the right skeleton and we've picked the right materials. But what do these things actually have to put up with? Now we're going to shift gears from the physical stuff you can see and touch to the powerful, invisible forces that are constantly trying to tear the plane apart.
The first force we need to talk about is load. Simply put, a load is any external force pushing or pulling on the plane, and we measure it in Gs. You've probably heard that term. So when a fighter pilot pulls a 9G turn, that means the plane's structure, and the pilot, by the way, is feeling a force that's 9 times the normal pull of gravity. And even on a commercial flight, hitting a bit of turbulence can put some serious G loads on the wings.
Now, when the plane experiences that external load, the material itself fights back. And that internal resistance, that fight, is what we call stress. It's the force inside every single little part, every rivet, every beam that's resisting being stretched or squished. It's like this invisible war happening inside the very molecules of the metal.
And the physical evidence of that war? That's called strain. When a material is under stress, it physically changes shape a little bit. It deforms, it stretches, it compresses. That physical change is strain. So next time you see a video of a plane's wings flexing up and down in turbulence, What you're actually watching is strain. You're seeing the battle between load and stress play out in real time.
So just how much force are these planes built to handle? Well, get a load of this. These are the minimum G-forces an aircraft has to be able to withstand in what's considered a survivable crash landing. The seats, the floor, the whole structure has to handle a forward force of 9 Gs. That's 9 times gravity without failing. It's all designed so that passengers have a chance to get out. It's an absolutely incredible safety requirement when you stop and think about it.
Okay, and this brings us to our last big idea. And honestly, it's maybe the most surprising one of all. Because the secret to surviving all these crazy forces isn't about being super rigid and stiff. No, the real secret is being designed to bend without breaking.
So, let me ask you a question. Imagine you have a long, skinny piece of metal, like a ruler. What do you think is the biggest threat if you start compressing it from both ends? You might think it's about just crushing it, but there's a different kind of failure that's way more sudden and way more dangerous.
And that failure is called buckling. Think about that ruler again. You push on the ends, and at first, it just compresses a tiny bit. It stays straight. But then you reach this one critical point, and wham! It suddenly bows out to the side. It's not a failure of the material's strength, it's a failure of stability. The whole structure just gives up at once. And this is why buckling is such a huge deal for engineers. The crazy thing is, a structure can buckle under a load that's way, way less than what it would take to actually crush the material itself. So a massive amount of design work goes into making sure this one specific type of failure can never, ever happen.
So how do they do it? How do they make sure the plane is safe? Well, they use a fundamental engineering idea called the factor of safety. It's pretty simple, really. They figure out the absolute highest load a part should ever experience in service, and then they deliberately design it to be much stronger than that. It's a built-in buffer, a safety margin that accounts for anything and everything, from tiny manufacturing flaws to freak weather events.
This whole idea leads to 2 golden rules of aircraft design. Rule number 1, the plane's structure has to be able to handle its limit load. That's the max force it's expected to see in normal flight without any permanent damage. It has to be like a rubber band. It can stretch, but when the force is gone, it snaps right back to its original shape, no problem.
But then you've got rule number 2, and this one is the real lifesaver. The structure also has to handle the ultimate load. That's the limit load times the factor of safety. Under this much more extreme force, it's okay if the part bends and stays bent, but it absolutely cannot break. It cannot fail. This is the rule that keeps the wings on the plane in a situation that goes way beyond normal.
So what's the number? What is that all-important factor of safety in aerospace? It's 1.5. That means every single structural component on that plane is designed and built to be at minimum 50% stronger than the absolute maximum force it's ever expected to encounter. 50%. That's your buffer.
So when you put it all together, you realize an airplane isn't just a stiff metal tube hurtling through the sky. Not at all. It's more like a dynamic, living thing, designed to flex and bend and absorb all these incredible forces. Its real strength doesn't come from being rigid. It comes from that controlled flexibility. And it kind of makes you wonder, doesn't it? What other amazing feats of engineering are out there, hiding right in front of us every day?